several of the previous videos, we talked about various ways of making color corrections in Photoshop. But before we go any further, I would like to make a side note and talk about something very important for photographers. I want to draw your attention to the fact that what you see on the screen when you make color and tone corrections may not be an accurate representation of what is really going on inside of the image file if your system is not set up properly. So as a consequence, your images may not translate well to other computers and may look different in web browsers or when printed. You should not skip this video and make sure to watch until the end, because I will also talk about viewing conditions, which is a topic often overlooked in discussions of color management. We said that if your system is not set up properly, that your workflow may be unreliable. So let's see what the most common problems are. For example, it is entirely possible that you edit and color correct your images on your laptop, but when you view this file on a different computer, the colors look significantly different on these two devices. The reason for this is because the laptop monitor and the desktop monitor are not tuned to the same brightness, and most likely display colors in a slightly different way. Another common problem you may encounter when printing on inkjet printer is that the output on paper may not accurately match what is displayed on your screen. The reason for this, once again, may be the fact that the screen and the printer are not in sync, but additionally, the problem could be caused by the fact that monitors usually can display a much greater range of colors than printers can print. So in this instance, there may be colors on your screen that the printer cannot reproduce. So there is a mismatch in the color gamut, or the range of colors, that the two devices can reproduce. These kind of issues are very important for photographers because it means that the images we publish on the web or supply to our clients can have undesirable color shifts and may not match what we see on our screens. However, it is possible to largely avoid these problems and get our color to be more consistent and predictable if we adopt a set of industry standards and practices into our workflow. These industry standards and practices are what in photography and digital imaging is called color management. Color management involves using standardized settings, profiles, and techniques to maintain color consistency across different devices such as cameras, scanners, computer monitors, and printers. This topic is very complex and it goes beyond the scope of this course, but nevertheless it is extremely important, so in this video I will try to explain the gist of the problem and suggest the steps we can take to arrive at a reliable Photoshop workflow. In the early days of desktop publishing and digital imaging, which was not long ago, we are talking about early to mid-90s, there was a lack of standardized color management protocols among different hardware and software manufacturers. This posed a significant challenge for professionals working with digital imagery, as images edited on one system would often look vastly different when viewed or printed on another system. So in 1993, 8 major vendors, including Adobe and Apple, recognized the need to address color management issues between different systems, and to tackle these challenges, collaboratively formed the International Color Consortium, or the ICC for short. The ICC took on the task of defining and putting in place a set of standards that would form the basis of a color-managed workflow that ensures consistent and accurate color reproduction across various systems and devices. So let's see how this color management system works. In a typical photography system, we usually have lots of input and output devices like cameras, printers, and monitors, and we want to set them up so that color translates accurately from one device to another. Communication and translation of colors between these different devices in a color-managed system is handled by a color management module, which is basically an app working in the background on your computer. Different applications and operating systems use different color management modules, but inside of Photoshop, the default color management module is called ACE, or Adobe Color Engine. In order to perform color conversions, the color management module uses what's called a reference color space. A color space is a specific three-dimensional model that defines the range of colors that can be represented or reproduced. It is a mathematical representation of colors, where each color is described as a numerical value or code within a specific system or context. The reference color space inside of Photoshop is called CIE Lab. This reference color space is not device-specific, but is meant to describe and map out the visible spectrum of light that our eyes can see, and acts like a reference book that all other devices can connect to and plot their color values against. So if we have the color management module with the color reference space on one end of the color managed system, on the other end we have individual input and output devices. What is important to understand is that different devices handle colors differently and vary in terms of the range of colors they can reproduce. This range of colors that device can handle is called a gamut. To add these devices to the system, we start by creating profiles for each individual device. A color profile is device-specific and describes how this device interprets and reproduces colors, or in other words, it defines its gamut of colors. Within the color management system, this profile acts like an ID that tells other devices what they need to know in order to sync with it. So for example, a monitor color profile tells the operating system and software how the monitor displays colors. It allows the system to adjust the colors sent to the monitor so they appear accurate and consistent based on the characteristics of that specific monitor. Apart from the reference color spaces that are device independent, we also have working color spaces that were made with specific purposes in mind and are not based on any specific input or output device. Because they are not device-specific, these working color spaces do not constantly change with time, like, for example, digital cameras change every year. Because they do not constantly change with time, the working color spaces provide a standardized editing space for images. Now let's see what the main working spaces commonly used in photography are. The sRGB color space was designed as a general-purpose color space that all consumer devices could adhere to. So if a computer manufacturer decides to make a screen, they have an industry standard to work to and make sure that their product can display the full range of colors contained within this color space. The sRGB is also a web standard and the only color space supported by all web browsers. Because it effectively acts as the lowest common denominator, this is the color space that all digital cameras default to. Adobe RGB 1998 is a color space that was adopted as an industry standard for professional photography. This is because its gamut is significantly wider than that of the sRGB. It closely matches gamut of a typical printing press, and nowadays high-quality computer monitors can also display full gamut of this color space. ProPhoto RGB is a very wide gamut color space that was designed to encompass an extremely broad range of colors, much larger than what is possible to display on most devices or even perceive by the human eye. Because of its wide gamut, ProPhoto RGB is sometimes used in professional photography because it has the advantage of preserving the full gamut of digital cameras' RAW files, or because it can utilize the full gamut of a printer. However, because it has a significantly larger gamut than standard color spaces like sRGB and Adobe RGB, images in ProPhoto RGB may appear oversaturated or distorted on average monitors, whilst printers may struggle to reproduce its full gamut. Earlier we said that different devices and color spaces have different gamuts, or the range of colors they can display or reproduce. For example, the horseshoe shape in this diagram represents the visible spectrum of colors that our eyes can see. If we superimpose different color spaces on top of this diagram, we will see that some color spaces like sRGB and Adobe RGB have smaller gamuts, while others like ProPhoto RGB have much wider gamuts encompassing a broader range of colors. Similarly, different devices and their gamuts may not always be able to match full gamut of a working color space. So for example, a monitor may only be able to show 85% of Adobe RGB, or the sRGB color space may not be able to cover the full gamut of a printer. To visualize this even better, on the Mac operating system, we have an app called ColorSync utility, which gives us a visual 3D representation of different color spaces. For example, this is a 3D representation of the sRGB color space. If we compare it to Adobe RGB 1998, we can see that the Adobe RGB 1998 is significantly larger than sRGB. And then if we compare it to ProPhoto RGB, which is also called ROM RGB, you can see that the ProPhoto RGB is much larger than the other two. It is also important to note the fact that if one gamut is larger than another, it does not necessarily mean that it contains the entirety of the smaller gamut. Very often, gamuts only partially overlap and intersect with one another. ColorSync utility allows us to compare profiles and color spaces. So if I click on Hold for comparison and then compare Adobe RGB with a printer profile, so let's say an Epson semi-gloss profile. So the grayed out area is Adobe RGB 1998, and the gamut shown in color is the printer profile. So you can see that Adobe RGB contains some colors that the printer cannot print, but similarly, printer can print colors that are not contained within the Adobe RGB 1998 color space. Now, you may ask yourself, if, for example, you send an image file whose gamut of colors is greater than that of the destination device, what happens with the out-of-gamut colors? To help us visualize and control conversions from one color space to another, Photoshop offers us a tool called soft proofing, which allows users to simulate how an image will look when printed or displayed on a specific output device, such as a printer or monitor. So, for example, if I go to View, Proof Setup, and then Custom, and then under Device to Simulate, if I choose, let's say, Fuji Matte Profile, this shows me roughly, this is a rough simulation of what this image will look like printed on this paper. I can also click on Simulate Paper Color, and this will try to emulate or simulate the contrast fall off when we translate our image from the screen to the paper. Now, if I click OK and go to View, I can turn Proof Colors on and off, or I can press Command Y to do this. Another thing I can do is if I go to View and then Gamut Warning, let's say that I try to saturate this image. So currently, all the colors are within the gamut of the printer, but let's say that I wanted to saturate these blues, the blue of the jacket, like this. This is just an example. So if I try to push these, then these silver areas signify or show the out-of-gamut colors. So to show the out-of-gamut colors, I would press Command-Shift-Y. Usually you would do this in reverse. If you see that you have out-of-gamut colors, you can go maybe to Hue Saturation or Selective Color Adjustment Layer, and then if I desaturate these blues, then I make all the colors within this digital file fall within the gamut of the printer. So there's less of a mismatch, and this makes it more likely that this image will actually print well on paper. If we go back to the proof setup, notice that we also have something called the rendering intents. In Photoshop, rendering intents are settings used during color conversions when moving a digital image from one color space to another. Each rendering intent governs how out-of-gamut colors, or colors that cannot be represented in the destination space, are handled during the conversion process. Two of the most frequently used rendering intents when printing photographs are perceptual and relative colorimetric. For example, perceptual rendering intent aims to preserve the visual relationship between colors, so it's perceived as natural to the human eye, even though the color values themselves may change. In other words, perceptual rendering intent squeezes all the colors into the new gamut. It preserves relationship between the colors, even though all colors may change slightly. On the other hand, relative colorimetric compares the extreme highlight of the source color space to that of the destination color space and shifts all colors accordingly. Out-of-gamut colors are shifted to the closest reproducible color in the destination color space. Relative colorimetric preserves more of the original colors in an image than perceptual. And this rendering intent is the default in Photoshop and is recommended for most color conversions, especially when most source colors are already inside the destination gamut. Now that we understand how the color management system works and what the main problems are, we can make informed decisions about the settings and color spaces to choose for our digital workflow. When deciding which color space to use, we need to consider the intended output medium and how our audience will be viewing the work. Photoshop's Color Settings dialog offers us a number of presets. Each of these presets recommends a working space for RGB, CMYK, gray, and spot. So first of all, let's have a look at some of these presets and the recommendation they give for the RGB mode. This mode is probably the most important for us because the images coming from digital cameras are in RGB. For instance, if we select the Web Internet preset, Photoshop recommends that we use sRGB as the working color space. This is because if the work will be predominantly viewed on digital displays and online platforms, then sRGB provides the best compatibility and ensures consistent appearance across a wide range of devices. In this example, I'm using the European preset, but you could select, for example, the American preset if this is your geographic location. This is not so important because we are going to tweak these anyway. If we select the pre-press setting, Photoshop recommends that we use Adobe RGB 1998 as the RGB working color space. This is because if the work is primarily for print or high-end photography, and we have control over the entire color managed workflow, then Adobe RGB 1998 offers the advantage of preserving a broader spectrum of colors. Apart from the sRGB and Adobe RGB 1998, we also mentioned the Pro Photo RGB, which is a very wide gamut color space. Some photographers like to use this color space when working with RAW files because of its extended gamut, and then later perform conversions to smaller color spaces if needed. One example where we could possibly want to use the Pro Photo RGB is if we wanted to print images to our own inkjet printer. If we compare the gamuts of semi-gloss paper and Adobe RGB, we can see that some colors of printer's gamut fall outside the Adobe RGB color space. So in this case, if we switch to working in Pro Photo RGB, which is also known as ROM RGB, or Reference Output Medium Metric RGB, we would theoretically be able to encompass the entire gamut of the printer. However, because the monitor may not be able to display all the colors inside the Pro Photo gamut, the print output may not be entirely predictable. So we could be required to do test prints and experiment with rendering intents until we are happy with the output. Another example where you could use Pro Photo as your working space would be, for example, if you were exhibiting or showing your images in a gallery or in a shop window on a wide gamut display that can take advantage of the ProPhoto RGB's wide gamut of colors. So going back to the color settings dialog, when selecting the RGB working space, we have three main options. sRGB if you are going to be publishing images on the web, Adobe RGB 1998 if your images are destined for printing, and ProPhoto RGB if your workflow is able to support this extremely wide gamut of colors, or if you are printing in a closed loop or on your own inkjet printer. When we pick an RGB color space, it's important to choose a corresponding gray working space too. This is because Photoshop's selections and masks work in grayscale. By selecting correct settings, we align the tone response curves of both the RGB working spaces and the gray working spaces. This means that the gamma curve, which represents the mid-tone contrast curve of our RGB color images, will correspond with the gamma curve of the grayscale masks and selections. As a result, our selections and masks become more accurate. As you can see in this example, if we stick to Photoshop's default recommendation by using dot gain of 15% as our gray working color space, then our masks may not accurately match our image. So in this case, using sGray would actually match the tone response curve of the sRGB image that we are working with. Now let's move to the CMYK working space option. As we said earlier, the most important working space is the RGB, because most of us now predominantly work with digital cameras which capture images in RGB. However, there are times when you may be required to convert your images to a CMYK color space because they will be printed by commercial printers in a brochure, catalog, magazine, or something similar. Photoshop's color settings come with generic CMYK profiles based on different regions. However, if you are ever asked to perform RGB to CMYK conversions, I would suggest that you liaise with the printer or designer and obtain the ICC profile for the actual printing press the artwork will be printed on. So for example, Condé Nast's Vanity Fair magazine has a page dedicated to technical specifications for submissions. Here we can download the ICC profile, which we can add to Photoshop by copying it into the Profiles folder on our computer. Similarly, if we were preparing our files to be printed in a book by Blurb, then we can download Blurb's ICC profile from their website, copy the profile to the Profiles folder on our computer, and then to convert an image to CMYK, we go to Edit, Convert to Profile, and select the profile we just installed. Now that we understand how color management works and have chosen the appropriate color settings for our digital workflow, the next critical step is to ensure accurate color representation by calibrating and profiling our monitor. To do this, we need a piece of hardware called Color Spectrophotometer, which is a color measurement device used to capture and evaluate color. In this example, I'm using the i1 by X-Rite. The software could be different if you are using a different device, but the procedure remains the same. So first of all, we need to make sure to turn off automatic screen brightness adjustment and power saving options in our operating system. Then move to the profiling software and set the white point of the monitor, which for photography should be set to D65 standard. The next step is to set the luminance level of the monitor depending on the final output of the images. For images that will be published on the internet, I would recommend setting the luminance to 120 candelas per square meter, and for images that will be printed, to 80 candelas per square meter. So in case you are wondering, this does in fact mean that your monitor luminance level should be set differently depending on the final destination of your images. Your monitor should be dimmer if you are preparing images for print, because this brings the screen closer to the paper. Then, after we set the luminance, the software will start displaying a series of patches to measure the monitor's gamma, white and black point, and color balance, and then correct them accordingly. Finally, the software saves a monitor profile in the relevant system folder. Color spectrophotometers are not cheap, so if you do not have access to one, although not ideal, you could try to guesstimate the luminance of your monitor. You definitely do not want your monitor to be set to its maximum luminance. And just as an example, luminance on my MacBook Pro is set to just over half of its range. And finally, after we have calibrated our monitor, we should also pay attention to our working and viewing conditions. This is something that most people overlook, yet is a crucial part of the color managed system. There's one exercise I used to do with photography students when we talked about color management. I would turn on the tungsten lights in the classroom and ask them to look at the white wall for about 20 seconds. And what you see on the screen now is a shot of a white wall. I would then ask students what color the wall is, and they would invariably say that it is white. Then I would suddenly turn the lights off and ask them, what color do you see now? This phenomenon, where an object appears to change its color depending on lighting conditions, is called metamerism. In this example, the black and white print in this book appears to have a warm tone under tungsten light, but if we switch to daylight, it appears to have a cold blue tone. The problem here is that we do not realize this until the two light sources are compared side by side, because our eyes and brains try to make color corrections. Because we expect the wall to look white, our brain tricks us into perceiving the color as white. It is also possible for two different colors to appear the same under certain lighting conditions. This is because a color is the result of interaction between the object itself, the light source illuminating the object, and the viewer observing the object. In this example, we have two different objects. Object 1 reflects red, green, blue, magenta, and yellow. And object 2 reflects red, green, blue, magenta, and cyan. Because these two objects reflect different frequencies of light, in daylight they would appear to be different color. However, because in this instance the light source is not full spectrum, because it emits only red, green, and magenta, the colors reflecting from these two objects and reaching our eyes would result in the same mix of colors, meaning that we would perceive these two objects as if they were of the same color. In this example, the red cloth appears to be very different color when it is illuminated by incandescent, LED, cool white fluorescent, and daylight light sources. For this reason, if we want to be able to reliably communicate color between different systems, we also need to standardize the illuminant or the light source used for assessment of color. The ISO 3664 of 2009 is an industry standard dealing with viewing conditions for graphic arts and specifically for critical evaluation and comparison of color prints. According to this standard, we need to make sure that the lighting conditions in our working space meet industry standards in terms of color temperature and spectral quality, light intensity, evenness of illumination, surroundings, and geometry. According to this standard, the recommended illumination falling onto a computer screen when working in Photoshop or assessing prints is the D50 illuminant. A standard illuminant is a precisely defined light source with a known and standardized spectral energy distribution. It serves as a reference for evaluating colors accurately and consistently across various devices and environments. Unlike general light sources, which can have varying spectral characteristics, a standard illuminant adheres to strict specifications, making it ideal for color-critical applications. The D50 lighting has the color temperature of 5000 Kelvin and a balanced spectrum, which closely simulates daylight. It is important to understand that not all 5000 K light bulbs meet the D50 standard, because the key factor in the light's performance is its spectral power distribution curve. So when comparing lights, we need to consider the color rendering index, or CRI, which is a measure of how faithfully a light source reproduces colors. Lights satisfying the D50 standards have a strictly controlled spectral distribution, which sets them apart from the general 5000 Kelvin light sources. Ideally, we should be using viewing booths, light fittings, and light tubes made specifically for the imaging industry, like these made by Just Normlicht. Consistent light intensity is critical to consistent image rendition, so this standard defines two levels of intensity. 2000 lux for critical image assessment and comparison, ensuring proper visibility of shadows and preventing overexposure in highlights, and the lower intensity level of 500 lux for practical evaluation of full tonal reproduction. This lower intensity level aims to simulate lighting conditions that the average viewer is accustomed to experiencing. Although this is not part of the standard, I would suggest that you keep the ambient levels around your computer monitor quite dim, to around 100 lux. This allows for better color perception and minimizes eye fatigue, while still providing sufficient illumination for comfortable viewing, without causing glare or reflections on the computer screen. To measure the intensity of ambient light, you may use a free app called the Light Meter LM 3000 by Light Ray Innovations, which is supposed to give you pretty accurate readings of the light intensity levels. For accurate image evaluation, it is crucial to have uniform and evenly distributed illumination without hotspots or uneven lighting. The evenness of illumination is expressed as a percentage of the specified light intensity, known as the nominal value. So for instance, in the case of print evaluation, the required illumination is 60% of the nominal value, meaning that if the specified light intensity at the center of the viewing booth is 2000 lux, it should be at least 1200 lux in the corners to ensure uniformity. The perception of color can be influenced by the colors of surrounding objects, whether through light reflected off of them or through their proximity in our field of view. To ensure consistent color evaluation, the viewing standard recommends using a neutral gray surround. While the specific L star or lightness value is not precisely defined, it should be a shade of middle to light gray, akin to a photographic gray card. For neutrality, the A star and B star values should be close to 0, indicating minimal coloration. So for example, you could set your custom background in Photoshop to lab values 5000 and make sure that your monitor surround is neutral. For prints, it is advisable to use a neutral matte surround with a luminous reflectance ranging from 10 to 60%, comparable to the Mansell N8 gray. This neutral background helps provide an unbiased context for evaluating the colors in the print, ensuring that the surrounding environment does not influence color perception. Glare can be problematic when assessing color prints, as it not only causes distraction, but also hinders the ability to observe reproduction details accurately. While the standard does not provide specific lighting geometry guidelines, it emphasizes that the positioning of the light source, image, and observer should be carefully arranged to minimize glare. Implementing the viewing conditions outlined above may be impractical and expensive, particularly for average practitioners without dedicated workspace. However, even if you cannot apply them fully, you could adopt them as a general principle to help you improve your color evaluation process. So, for example, you should try to do all color corrections during daylight hours and never under tungsten or fluorescent bulbs. Additionally, you should be mindful of the ambient light levels when working and assessing prints, opt for neutral gray surroundings, and make sure to avoid glare and reflections on the computer monitor. As I said at the beginning of this video, the subject of color management is very complex and goes well beyond the scope of this Photoshop course. If you would like to learn more about it, I would suggest 2 books. The Real World Color Management by Bruce Fraser, Chris Murphy, and Fred Bunting, and Color Management for Photographers by Andrew Rodney. Both of these books are out of print and slightly out of date, but nevertheless the gist of the color management theory still remains the same, so they are still a good read. I hope that this video gave you a comprehensive introduction to color management, and that you now appreciate why this is an important subject to understand. While the concepts outlined above serve as valuable guidelines, it's important to recognize that these are not rules. Different photographers have different working practices. You can, for example, use different settings when printing different images, or do tests to see what gives you the best results on an image-to-image basis. However, by gaining a comprehensive understanding of color management, you can make informed choices within your Photoshop workflow, and in this way ensure color consistency across different devices.